I am Archie Jarman, and I'm the program officer here at the Horticulture Innovation Lab, and I just wanted to welcome you all to the Horticulture Innovation Lab's Network Webinar Series. Today, we are excited to have a stellar panel of experts who will be presenting this webinar titled Dry Chain, a solution to dried commodity losses due to moisture and humidity. Some logistical items for the webinar. Please use the chat button in the toolbar at the bottom of the Zoom window to introduce yourself, as Brenda's been guiding you. And for any technical difficulties, please also use that chat room. For questions, we will have some time at the end of the webinar to answer questions. Please type your questions into the Q&A button, also in the toolbar at the bottom of the Zoom window at any time. And again, we'll answer those at the end. The webinar will be recorded and made available along with the presentation slides. Now to introduce our panel. Kent Bradford is a distinguished professor at UC Davis and the director of the Seed Biotechnology Center. His research interests span diverse areas of seed science, from seed germination and conservation to mathematical modeling and molecular biology. He has published more than 170 peer-reviewed research and extension articles and book chapters, co-edited 3 books, and co-authored a textbook on seed development, germination, dormancy, and storage. James Thompson is an emeritus agricultural engineer in the UC Davis Department of Biological and Agricultural Engineering. With the Horticulture Innovation Lab, his focus has been to develop technologies for reducing post-harvest loss of perishable fruits and vegetables and dried foods. Michael Reed is the Horticulture Innovation Lab's leader for innovation and technology. In this role, he identifies and develops new technologies that address constraints to horticultural production and marketing by smallholder farmers in the developing world. Anthony Phan is responsible for scaling commercialization of the DryCard technology in developing countries. He also supports program systems and activities for our management team. And finally, but not least, Rana works as an associate researcher on a Horticulture Innovation Lab project in Bangladesh focused on examining nutrition impacts of horticultural innovations. His work focuses on implementing and testing Horticulture Innovation Lab technologies in the field level, along with analysis of the technology's social and economic impacts. With that, I'll turn it over to Kent to start this great panel.
Here we go. Did you do it or did I? Okay, good. Okay, so what I'd like to start with is what the problems are that we're trying to address here. And various estimates have been made, but a lot of them center around the idea that about a third of food produced in at least certain developing countries is lost before reaching the consumer. That means problems at the harvest stage, but particularly the post-harvest handling, storage, distribution of these crops. So that means a lot of effort has been put into the production of these foods that don't make it to the consumer and end up essentially wasted. In developed countries, a similar scale of loss happens post-consumer, but we'll be dealing with this front end for the most part now. The other aspect of this that we'll be dealing with is that as a consequence of poor storage, fungi that can produce mycotoxins such as aflatoxin are often present in these stored commodities. It's been estimated that over half the people in the world are consuming aflatoxin in their diets. There are guidelines for the limits for content and so on, but those vary around the world, and often testing is not done. And in other cases, those spoiled grains are fed to animals, but the aflatoxins can make it into meat and other products, milk products particularly as well. So those are primary issues that we want to deal with. An increasing fraction of the world population actually lives in areas where high humidity is the norm. That is, if we look at the central tropical band around the equator, high humidities are common there. We'll show you a slide in a minute of how this changes in various parts of the world. But when you look into studies and reports on post-harvest losses, particularly in dried commodities, it's generally said that this is a problem with storage, but it's not really go much beyond that. That there are many strategies to try to prevent these fungi from growing and so on. But unfortunately, a lot of them seem to neglect the basic problem, which is the high humidity, high moisture content, and continuous high temperatures in that part of the world. This shows a movie. It's over a period of time, but it's showing a color graph of humidity. The blue is where it's most high humidity. And you can see, for example, in South America and Congo region and Africa, it's high humidity all the time. Southeast Asia. Well, you look at India, and you can see that we have a wet season, dry season situation where it's very wet certain parts of the year, dry other parts of the year. So these are the areas where we have the most problems with this. The very northern regions are also showing a lot of humidity, but it's also cold. So they have a very different storage type situation. So here's a figure that shows the relationships between temperature, commodity moisture content. This is showing maize, for example, and the equivalent equilibrium relative humidity. And Jim Thompson will talk in a little bit about the relationship between those. But this graph is showing a few points, which is that across a pretty wide range of temperatures, you can get fungi, insects, other bad things to grow. But the key point is that as you lower the moisture content or equilibrium relative humidity, certain organisms are unable to grow below a certain point. So at very high moistures, of course, bacteria, fungi, insects can grow, and at very, very high moisture contents, of course, things like seeds will germinate. Much considerably below that, but still in a pretty moist range, say between 90 and 65 or 70% humidity, the fungi and insects can still grow. And for example, if you look at the left side, around 13%, 12 or 13% for maize is often recommended as sort of the target point for drying maize for good storage. And you see that's just at that point where you prevent those fungi from growing. Insects can grow down to somewhat lower water activities or relative humidities. But eventually, if you dry things enough, really biology basically stops and you don't have these problems. So that's the point that we're trying to make here, is that most of the problems in storage, molds, insects, and the mycotoxins that they produce would be prevented if we were able to store products in a dry state. Maybe a little hard to read, but I'll just point this out to you. When we look at the losses post-harvest, we often focus on fresh products, fruits, vegetables, roots, tubers, and so on. That's the right circle. And what it shows is that a large fraction by weight of losses, post-harvest losses, are constituted by that fraction. We'll talk about why that is in a moment. If you look at the left-hand graph, though, this is showing the losses by calories, or you could think of dry weight. A lot of the loss in weight, of course, a lot of the weight of those fresh products is really water, and you do lose a lot of weight when those things are spoiled in post-harvest. If you look at the calories, though, on the left side, you find it sort of reversed. That is, about 60% of the calories lost are actually in the cereals, grains, legumes, and so on. So preventing this post-harvest loss in both categories is very important. And we have a lot of attention and strategies on the fresh produce side, but surprisingly less on the dried commodity side. So what do we do with fresh produce is try to implement the cold chain. So the cold chain is the term we use for a process of harvesting fresh produce, refrigerating it as quickly as possible, and then maintaining that temperature, low temperature, throughout the whole process. That means refrigerated transport, refrigerated storage, warehouses, and so on, all the way to the consumer, refrigerated shelves in the supermarkets and so on. So it's called a chain because every link along the way has to take care. That is, if there's any break in that chain, if the product is allowed to warm up, that's pretty much it. It's very hard to recover from that, and there's losses. So we call it the cold chain because you need to get the product cold and then keep it cold throughout the marketing system. If we look at this cold chain, in fact, this post-harvest situation on just two axes, that is warm or cold, or wet or dry. most foods start wet and warm. That is, they're plant products, animal products. They're wet and warm, which generally equivalates to poor storage. So the cold chain was created for fresh produce. You don't really have the option to dry fresh produce. Well, you do in certain fruits and so on. You can do that, but for what we call fresh produce, it needs to be wet, moist, and so really your only option is to implement the cold chain, which is great, but requires a lot of infrastructure, refrigeration, a lot of energy to maintain. So that's why it's lagging in certain parts of the world. If we look at products that can be dried, as we mentioned, lots of cereal grains, legumes, and so on, just drying itself provides pretty good storage. That is, even at fairly warm temperatures, if they're dry enough, then they have quite a decent lifetime. You maintain quality, prevent adverse things from happening, and also maintain nutritional quality. Another big advantage is that once these are dry, and if you package them to prevent reabsorption of water from the atmosphere, then there's no further cost. That is, you've invested the effort into drying and packaging, and there's no further infrastructure cost except maintaining the integrity of those packages. This is what we call the dry chain. So it's a fairly obvious term, but apparently had not really been applied to this aspect of post-harvest, but it's directly an analogy to the cold chain. So if we look at the combination, dry and cold, of course, that's very good for storage, for things that can be dried, long-term storage. It's excellent for seeds, germplasm storage, and so on. But then again, you're back into costs for refrigeration or freezing, and so on. So these are really the options that we have for post-harvest storage. Of course, to get there, we have to have drying of the product, and we'll have a discussion on. Mike Reed will talk about that in a moment. Almost everywhere, sun drying is used. That is at least a certain stage of sun drying, where they're standing crop in the field, harvesting and putting out, and allowing it to dry in various ways. Also, we have heated air dryers and other types of mechanisms that we'll talk about as well. We'll come back to that later. Once the product is dry, particularly in these humid regions, it's important that those commodities be protected from the atmosphere. This is the part that in our projects we found that really awareness was not as high as you would expect in the areas where it's most important. You have ambient humidities of 80, 85, 90%. All times, the commodities will reabsorb moisture from that atmosphere. Their moisture content will increase, even if you've dried them already, will increase up into those dangerous poor storage areas. So it's important that, and a key part of the implementation of the dry chain in humid areas is that those products, once they're dry, get put inside various types of containers. There's many of you may be familiar with the PICS bags that are also oxygen resistant, but the moisture content, the moisture-proof aspect, is another key part of those PICS bags. Also, there's various types of metal or plastic bins, and there are also very large-scale packaging for large commodities through super bags, grain pro bags. These were started at the International Ration Research Institute and have been commercialized as well. So here's the basics of the dry chain: harvesting and then drying. So that it needs to be dried in some way, whether it is air drying in the sun or artificial methods we'll talk about a little bit later. It's important then to package and store those. This is showing, for example, high-value seeds have long been stored in metal cans. There are various ways to protect them during shipping and distribution. Transportation, the key thing here is to maintain that packaging and transport the products as well. And then be sure that they end up either with the farmer for planting or for the customer for consuming in good shape. Things not to do are not to store moist or bulk seeds or grains. That creates spots of high humidity and allows fungi and insects to grow. Don't use porous packaging. This is the biggest issue, I think, is the first picture I showed you, huge mounds of wheat stored in burlap bags, which means they're porous, which means that air will get through them and moisture will come with it, and they are not protecting the product from the environment. Plastic woven bags are no better. That is, they're used a lot. Polyethylene bags that are woven, like cloth, are used, but they are not waterproof. Don't leave the packages open. I've been to many, particularly seed markets or grain markets and so on in the developing world where there's a big bag of seeds or grain and it's just sitting there open. This is hard habit to get out of, but that's allowing moisture to get into those. And those who get the bottom of that bag will probably get more moisture rain than the top. And here's a picture of, you know, a lot of commodities are transported in bags in the developing world. If they were waterproof, we'd be better to leave them in the bags than dump them out like this and allow them to be accumulated in contact with the atmosphere. So that's the basics of the dry chain. Basically, it means to make things dry and then keep them dry. And you can find on this website reports from our project with the Port Innovation Lab on this and further tools and things for working with this. So, am I going ahead with this now? We're going directly into, I guess we're going into drying methods.
I guess Jim's going to talk about water. I think that's coming in a few minutes.
Okay. Change the order just a little bit. So we're going to switch over into drying methods, and I'll start out with you know, one approach that we worked on, and that is part of our project, is a somewhat novel one. It's using desiccants rather than the other strategies, and involves drying beads, which are a desiccant that was developed by Rana Research, Johan van Osbroek at Rana Research in Thailand. It's a zeolite type clay material that, when heated in certain conditions, forms a crystalline type structure that forms microscopic pores that will hold water molecules very tightly. So basically, it's like silica gel. I'll show you in a moment, but it binds the water more tightly, better for reducing moisture content to low levels. So basically, the process is to enclose these desiccants along with the commodity inside of a sealed container of some kind, something that will prevent transfer from moisture from the outside. And the water will move into these beads and be trapped, and it will evaporate from the commodity. So we'll just dry the commodity simply by the diffusion of the water from the commodity into these beads where they're trapped. These drying beads can then be reheated to reactivate them. They're crystalline, so the water basically is lost, and they're fully reactivated to reuse again. So this shows that I mentioned these beads. This is the sort of crystalline structure that holds water molecules. And this is a comparison with silica gel. That's the red line, which shows that at very high humidities, silica gel will hold more water. It's a good absorbent at high humidities. But if you go to low humidities, it does not hold very much. That is, it holds less tightly, and therefore you would have to reactivate a certain quantity of silica gel multiple times to get moisture contents down quite low. The drying beads have a very different pattern, where they essentially keep the humidity very low until they're full. And then once they're full, then the humidity can rise. And so they can take commodities down to quite low moisture contents as long as there's excess beads around. So this requires some types of containers and scaling up. So it can be used quite well for small quantities, seeds, breeding materials, things like that, different sizes of plastic or other types of boxes. You can see those have a little humidity meter in there to just monitor the situation. Larger scale are like these metal barrels that have been built specifically for this purpose, usually about 50 kilogram barrels. Through the center of those, there's a column, screened column that beads can be introduced to in a cylinder that makes them easy to insert and take out. This reduces the diffusion distance, and the moisture from the commodity will move into the beads. Then you can take the beads out, reuse them, and just seal that container to maintain low moisture content. Then you need an oven of some type, various different ones for larger scale, smaller scale. For these barrels, there are specific ovens that have been identified where you can just slide those cylinders of beads into them and reactivate them. So the basic concept of using these, go back to the basic dry chain. You need to harvest and dry, and of course, it's good to take advantage of air drying as much as possible. What we find, though, is that in those humid climates, often that's not sufficient, and you need further drying. And this is where these desiccants or other methods we'll talk about come in. That is to get the commodity moisture content down below that threshold of about 65 or 70% equilibrium relative humidity, where they'll at least be safe from the molds and so on. Further drying is good for even longer storage and maintenance of quality. And then it requires, as we mentioned, various scales of containers to maintain them after that. So here's a decision chart. Here's a paper that has a lot of this information in it, so that would be a good reference to go to. Basic decision chart for deciding what to do. If the commodity can be dried in the open air, for example, in certain areas where you have monsoonal and dry season. In the dry season, it's very hot and dry often. The commodity is perfectly fully dried in the field. But if they're not packaged for the subsequent monsoon, then they'll suffer problems. So what it shows is if they're already dry, just package them and you've initiated the dry chain. If you test the moisture, and we'll talk about that in a moment, it needs additional drying. You can use sonor air drying, or you can use heated air desiccant drying until you get the moisture content down to a safe level. Then implement the packaging and storage. So as we mentioned, I'm more of an advocate of packaging than controlled relative humidity facilities. That's very expensive in humid climates to maintain warehouses or buildings at low RH. So I think the packaging is a better way to go. So a few places have done this already. For example, we've worked with some community storage location systems in India and in Nepal, for example. Bioversity International, a CGR center, has implemented these on community germplasm storage banks and so on. The picture on the left shows these clay pots and so on. Often these are not airtight, really. So switching to something that really is airtight, using, particularly in this case, drying beads are quite convenient because you can keep all the samples separate and dry them individually. Works quite well. Here's an example working with Denise Kostic, who's the head of germplasm conservation at CIMMIT in Mexico. She's implementing a lot of these tools in the system with CIMMIT. But this is some work she's doing in Guatemala with small communities storing their maize for the next year. And here she's using the DryCards, which you hear about in a minute, a quick indicator of humidity. At the top is when they started. The blue means that the cards were dry. They put them in with these seeds for an hour or so to seal them up, and they're all pink. So what that means is that they were in fact storing their commodity, their seeds at too high moisture content, and they're not going to have great success with those storages. And so, bigger scale, this is they call it a low energy gene bank in India, where they've implemented these tools. No refrigeration, but bringing germplasm here, drying it very dry, using particularly these drying beads, and then putting them in sealed containers, and not worrying so much about trying to refrigerate them or dehumidify the system. This is not an indefinite storage, but it's good for intermediate term storage, and would be adequate for most breeding programs, for example, for their annual up to 3, 4, 5 years storage of their products. So I just mentioned scaling up. So we did have a scaling up project in Bangladesh, starting with particularly high-value seed companies producing vegetable seeds, hybrid tomatoes, hybrid peppers, other types of vegetable seeds. This was implemented by Rana Research, our colleagues over there. And some companies, 3 companies at least, fully implemented this method, and a number of others are implementing as well. And you can see the scale that they're doing this up to. Lal-Tier is a very large company that's expanding now to be handling up to 25,000 kilograms a year. This is their CEO saying that basically they tested this system. Our project from the Mohd lab focused on training their employees multiple times as they implemented this to be sure that they were doing everything the best possible way and dealing with their contingencies as they came up. And in 1 year, they realized that the fact that seeds that they stored this way had not lost viability, were still sellable after a year. Not throwing away those seed lots basically paid for the entire project in the first year. So they're fully committed to this project. So this is showing this scaling up project, and we've taken this opposite approach that we started from the top down. We started with the company who had the need for better preservation. We've trained experts from the companies. They in turn trained trainers through their system, who who then trained contract seed farmers to implement these methods. That is, basically, they sent farmers containers and dry beads. When they harvested these seeds, these hybrid seeds, they put the seeds in a container, added the beads, sealed them, and just sent them back to the company. The company gets the beads back, reactivates them, uses them again, and they don't have to have a big investment in heated air dryers and so on. They get dry seeds back, and they just keep them that way. And if you calculate the number of potential farmers who could get better seeds from those seeds that were produced, then you get back to the numbers. So this is a much more efficient way, we think, than trying to go out to farmers directly. That is, our concept would be that a lot of the implementation should come from upstream seed companies, commodity traders, and so on, who will get the benefit of improved quality for relatively smaller costs invested on the front end. So that's initial overview of the dry chain, and I'll turn it over to Jim now for the background on the technology, the details of the physics I was just describing.
Thank you, Ken. So let's back up a little bit now and take a look at this concept of water activity and how it influences quality of our products. Two ideas. First is, Ken mentioned the word equilibrium relative humidity. I also want to talk about the concept of water activity. They're very similar. They're the same idea, basically. If you take a product, put it inside of a sealed container, the headspace will achieve an equilibrium relative humidity based on the moisture content of the product. So that headspace humidity is called equilibrium relative humidity. For maize, for example, when it's at a safe storage moisture of about 13.5%, roughly, it will correspond with an equilibrium relative humidity of about 65%. And we also use the term water activity. This is more used in the food science area, but same idea, and it's simply equilibrium relative humidity divided by 100. So 0.65 water activity equals 65% equilibrium relative humidity. We'll switch to mostly talking about ERH from now on, but it shows that idea. The key idea then is if we measure the humidity of the air above the product, we'll understand its moisture status. I'm not going to say. Now, this is a graph that shows the effect of water activity on the bottom versus various biological activity. So you can see on the bottom right, those sharply descending lines show the growth rates of molds, yeasts, and bacteria. At water activities above about 0.7 for molds, for example, they have significant activity and are growing. And of course, that's the key issue that we've been talking about with mycotoxins. We want to prevent those molds from growing. And certainly also mold growth produces physical loss of product, loss of mass, and the product just simply doesn't taste good. On the other lines show other sorts of biological or chemical activities that are occurring, enzymatic browning, non-enzymatic browning, and lipid oxidation. They're still at fairly high levels at 0.7, 0.75. So we do see this, in fact, in long-term storage of dried products. Dried fruits will brown and change color in storage. If we were to dry them to lower water activities, the rate of those changes would be reduced. We typically don't do that, though, because it takes a lot of energy to dry significantly below about 0.7 water activity. So for large-scale storage, we don't do that. The key point of this slide, though, is that if we can keep water activity below about 0.65, we're going to stop the growth of microorganisms. This is another graph that's a repeat of similar ideas that Kent showed you, but in this case, we're looking at fungal growth. This is a generalized relationship. It shows the effect of temperature and relative humidity. So where our focus is in the humid tropics, where temperatures tend to be relatively high. We'll use something like 30 degrees Celsius or so. And you can see on the germination time graph on the left that at a water activity of about, or equilibrium relative humidity of 90%, takes about a day for the fungal organisms to begin to germinate and grow. On the other hand, if the equilibrium relative humidity dropped to about 0.75, now it takes 10 days, or 10 times as long. If it drops to 0.7, now we're approaching 100 days, or 100 times as long at 30 degrees. Now, if the temperatures are lower, the germination rates are also lower. But as we've discussed, we're typically not going to control temperature in dry storage. If we need to, we can do that, as Kent mentioned, for seed storage, where we want storage times that are extremely long, years, rather than months. The graph on the right shows growth rate. That's the rate of growth of the organisms. And you see a similar relationship. At 90% equilibrium relative humidity, we're seeing a growth of 2 millimeters a day in a petri dish of the organism. If the equilibrium relative humidity drops again to about 0.75, now we're down to about 0.5 millimeters, dropping again to the levels we're really after at 70% relative humidity or lower. Now we're down to just 100. So it's 100 times slower when we reach these low levels. It doesn't show data down at 65%, where we typically store, and the growth rates then are virtually zero. In long-term storage of months for dried products, we will see no development of microorganisms. So the point is clear in this. We want to have equilibrium relative humidities below 65% for safe long-term storage of food products. We want lower levels for seeds, but for food products, 65% will work very well for us. Now, we will talk about the dry chain and product dryness, but many people are interested in the idea of moisture content. Can we use equilibrium relative humidity to measure moisture content? And the general idea is we can estimate it, but we can't predict it precisely. This shows a simplified graph for cocoa beans. And you can see at a relative humidity, the key number there of 65%, the moisture content of the cocoa beans is about 7%. For maize, that will be 13.5%. Every different commodity has a different relationship between the critical equilibrium relative humidity and the critical moisture content that is associated with it. And that's one of the real values of using equilibrium relative humidity, because it by itself, that single number of 65%, works for everything, independent of the equivalent moisture content of the product at that humidity. Now, the exact relationship between equilibrium relative humidity and moisture content is affected by product temperature, and you will see graphs that indicate this relationship. It's also dependent on whether the product is drying, desorbing water, or gaining water, adsorbing water. There's a difference in the relationship between those two processes. It can depend on the cultivar of the product, growing conditions, drying temperature, particularly high drying temperatures, change the equilibrium relative humidity moisture content relationship. Some work that was done by Rice in Taiwan, an extensive study, showed that when you can control all the variables above there, you can use equilibrium relative humidity to predict moisture content within a range of about plus or minus 0.5%. If you don't control those factors above, the relationship is much less accurate. So we tend to not want to use the concept of moisture content, but stick specifically to equilibrium relative humidity. Now, before I leave equilibrium, go to equilibrium relative humidity, let's discuss some of the other issues about measuring moisture content. Its big advantage is that it's fast. Typically takes a few seconds, less than 10 seconds to measure moisture content. Some of the units can be handheld, portable, cost less than $300. They'll have an accuracy, a relatively low accuracy, somewhere in the neighborhood of plus or minus half a percentage point. Benchtop units on the bottom there, they cost anywhere from $2,000 to $5,000, have greater accuracy, potentially down to plus or minus 1/10% of moisture content. But to achieve that, they need a separate calibration for each product in each growing location. And in fact, if you go to the manufacturer's websites, you'll see, in some cases, hundreds of calibration curves for various products. For maize, you may see 20 or 30 calibration curves based on location and sometimes cultivar. The other critical issue, though, is to obtain a representative sample. You can't just grab a handful of product from a bag and assume that that handful represents the moisture content of the entire bag. You have to sample product from the entire volume, and that's its disadvantage. Now, the other concept that we can use is equilibrium relative humidity. And this shows you some of the work that we did where we developed the DryCard. This concept, it uses a relative humidity strip, a paper strip that's been saturated with cobalt chloride. And cobalt chloride naturally changes color based on the humidity around it. And you can see those small vials on the bottom. At low humidities, the strip is dark blue. As the humidity increases, it changes to sort of a mauve color. And at that critical 65% relative humidity, it's approaching a bright pink. At 75%, it's a bright pink color. The nice thing about this then is that we have a clear indication of excess high levels of equilibrium relative humidity when that paper strip turns bright pink. When it moves away from the bright pink color towards the mauve and the grayish bluish color, then you've got a safe equilibrium relative humidity. So the DryCard then becomes the critical tool that we can use to manage moisture content of any dried commodity, grains, dried fruits, nuts, dried fish, meat, anything. The other options for measuring equilibrium relative humidity are a hydrometer. There are small, relatively inexpensive hydrometers you can see in the middle there. They cost retail somewhere between $3 to $10 a piece. They work really very similar to the DryCard, providing exact same information. We'll talk a little bit about using both of those in a minute. The other alternative is a water activity meter used in the laboratory. It's extremely expensive, however. It produces results that are in a faster time, anywhere from 1 or 2 minutes to 5 minutes, depending on the product and the condition. On the other hand, the DryCard and the hydrometer will take minimum 20 minutes, perhaps an hour to give a reading. But of course, they're much less expensive, portable, easy to use. The DryCard itself is inherently calibrated because we're working with an inherent property of cobalt chloride. Hydrometers do need to be calibrated. They can go out of calibration. Sometimes if they're exposed to liquid water, high temperatures, rapid fluctuations in humidity and temperature conditions can cause problems. So they do require some calibration periodically. Now, how to measure equilibrium relative humidity. It's a simple idea. We're going to measure the humidity in the headspace of the product. If we want precise readings, it's going to take 4 to 24 hours depending on the product size. This is particularly true after drying because the product goes into storage where the moisture is not equilibrated within the product itself. During drying, it's got low moisture on the surface, high moisture in the interior, and it takes time for the moisture to migrate to the surface and equilibrate. So it will take some time. Another critical idea, though, is that we want uniform temperature. So the dry chain depends primarily on moisture, the moisture content of the product. But within a storage volume, particularly large volumes, if you've got relatively cold areas compared to relatively warm areas, this may be, for example, in an open storage like Kent showed earlier, the sun's shining on the exterior bags, heating that product up, the interior is cold, it can cause high relative humidity in the colder product. So we generally want to maintain uniform temperature also. The other issue then is the DryCard hydrometer needs to be exposed to the headspace, conditioned for 30 to 60 minutes for approximate determinations. Overnight gives you a precise determination. So that means, for example, when products are being dried in sun drying or in solar dryers, the product is oftentimes brought in at nighttime, place the hydrometer or the DryCard in the storage bag, and next morning you'll see clearly whether the product has been adequately dried. Michael Reed. At the end.
So Kent and Jim have talked about the background and theory of the dry chain. I think one of the interesting things about the DryCard that we like to say is it's like a thermometer. In the cool chain, a thermometer is the essential unifying tool. It tells you what the temperature is. The DryCard is like a thermometer for the dry chain. It tells us what the water activity is. Kent mentioned the dry chain. The concept of links in the chain, each link is critical. The weakest link is going to determine how well the product stores. So the links are from harvest, drying, then storage, and finally transportation and sale. Storage is a key link in the dry chain. Ken has already mentioned that proper storage maintains quality of grains and pulses, prevents mold, stops insect damage, and prevents rodent and bird attack. And I'm sure nobody thinks that this is a good way to store product, but many people figure that nice bags like this are indeed a good way to store product. Ken has already mentioned why that's not true in environments where humidities are high. Products in those bags can not only be attacked by insects, but also can be accumulate mycotoxins such as aflatoxin, which is such a critical health problem globally. It's critical to maintain the dry chain, to keep storage below 0.65 water activity, prevents fungal infection and reduces insect attack. And to do that, we need to store in hermetic containers. These containers need to be sealed. They can be plastic bags or drums. They can be steel canisters or silos. And the benefits of hermetic storage are not only that it reduces or prevents the uptake of water from humid environments, but also that insects that may be infesting the grain rapidly deplete the oxygen that's available to the insects. So they actually breathe, use up the oxygen through their biological activity. And that low oxygen prevents additional insect damage and may reduce mold growth too. So in fact, the insects, when they're sealed in a plastic hermetic container, kill themselves. Here's some examples of what happens in a sealed bag with some insects in the bag during the storage period. Very rapidly, early in the storage, the oxygen content of the bag reduces from the 21% in air down to about 5%. Correspondingly, the carbon dioxide, which is produced by the insects during respiration, increases. And here are some data from a study where people put in these are chickpeas placed in fixed bags. The seeds were either infested with insects or not infested. So the infested ones, they actually added insects to make sure that they had insect activity. As it turns out, there were insects even in the non-infested pigs. And then we've got a comparison of polypropylene sacks that Ken mentioned. Those woven polypropylene sacks do not prevent the uptake of moisture and do not seal against exchange of gases, non-infested and infested. And what you clearly see from these data are that A and B, the non-infested PICS bags, so the sealed bags, whether they were infested or not, the A and B lines show that there's no live weevils in the sacks after 6 months of storage, whereas in the others, the polypropylene sacks or even insecticide-treated seeds, you got a substantial increase in the number of insects and damage from those insects in the bags. So the key concepts for storage is storing the products below 0.65 water activity, slows quality loss, and prevents insect and decay damage. And that hermetic storage can prevent insect infestation and mold growth by maintaining low water activity and reducing the oxygen concentration. And that hermetic storage containers are an essential link in the dry chain.
All right, now going back to the DryCard, to make the DryCard more well-known and widely available, the Horticulture Innovation Lab is working with businesses and entrepreneurs to set up in-country manufacturing, marketing, and sales of the DryCard. DryCards can be made using locally available equipment and materials for just 15 cents per card and can be sold for over $1 each. This offers a great business opportunity while still maintaining an appropriate price for smallholders. To become a DryCard entrepreneur, we first request a business plan that details plans for DryCard production and sales. If the plan is approved by our team, an agreement between the company and the Horticulture Innovation Lab is established to set guidelines for manufacturing, reporting, and providing technical support. The Horticulture Innovation Lab then provides the necessary resources needed to begin production, including a starter package of materials, which is enough to produce 10,000 DryCards. Once that package is received, entrepreneurs can begin manufacturing and marketing the DryCard in their country. Since August 2017, we have set up DryCard entrepreneurs in 10 countries. Some of the businesses that we have partnered with are social enterprises, consulting companies, and ag input suppliers. To date, these entrepreneurs have sold over 22,000 DryCards and have expanded their businesses to include other post-harvest technologies such as PICS bags and aflatoxin test strips. If you or others in your network are interested in working with the DryCard, please contact me. Thank you. So it looks like we're going over to Rana.
So yeah, sorry for the inconvenience. Now I'm gonna show the drying chain in Bangladesh, like what we did for improving the drying chain. The next slide. Yeah. Next place, Anthony. Sorry. Yes, these are the like commonly dried product in Bangladesh. These are chili, fish, pulses, cereals, mango, and groundnut sunflower. And this like in the shown in the picture, things are dried in Bangladesh. They just put the product in the floor and in open air. And for steering, they sometimes use their legs or like some stick to steer the product. Anthony, please, next slide. And this is their traditional way of packing and storing. This in the first picture, you see they just put the dried fish in a room and just lay them on a floor. And these fish should be packed by maybe 2 days or 3 days later. And in the second picture, they are now packing the fish. You can see that a person is literally inside the bag. He is just compressing the fish with his legs so they can put more fish in one bag. And this in the next picture, a woman is showing her dried chili and how they store the dried chili in their home for their household use. And for for getting the sense of the like how much drying is being done or what is the proper amount of drying, they actually depend on their sense, like the color, scent, and aroma. And sometimes they also touch it, like by touching it they can feel the moisture with their hand, and sometimes with the sound when they breaks, like a brittle sound created. And with that sound they have a sense, because earlier they have tried their product and they are hello.
Hey, Rana, we're just switching the view real quick.
Sure.
Perfect.
So it's
Thank
been done. I mean, the next slide. Oh, yeah, yeah. And now here comes our project approach for for having them access to the better drying. So we from our project we built three chimney dryer in three communities, and these are the kind of pictures. Please go on to the next slide. Here we have trained almost 40 people on building and drying the chimney dryer, and also introduced DryCard on determining proper drying. Here in the picture, you can show that we are giving training to the very local people in the. It's a very rural area in Bangladesh, and uh, these are the products being dried in these are the different picture. Is this in the this is the unusual sun dried, and this is the UC dried. You can visually see that quality is looking better when you dry product with the chimney dryer. And Anthony, would you please advance? There's something. Yeah. And these are the perception we got from the farmers. They said it's easy to construct. It can dry faster when they dry product in our chimney dryer. It keeps food safe, closed and protected from the dirt and dust. Next, Anthony. And it gives better color and smell and taste when they dry it in the chimney dryer. And this is next slide. These are the some data we have collected, and we from our analysis we have we are doing the economic analysis for each and every technology, and this data pretty much we've got from there. Like this is the total amount we have dried in 3 years, and these are the market price like in 3 years from 2016 to 2018. So all the cases you see that when they dry chili and fish, they are getting good price in like almost twice or thrice than the fresh product price is. I mean, they're getting a good price. So these are the products they need to dry, and they have already established market. So there's a demand for this product in the market. Next slide. And challenges like before implementing, like when we do at the very beginning, that time we didn't have any handy manual, so it's tough for us to understand people that what is the technology and how it works. Even it was tough for us to make the carpenters to understand the design in building the chimney dryer. And another challenge that we faced, and we're still facing this challenge, we in our country, like in the rural area, we don't have sized wood, and these woods are not seasoned. So it's very evident that many times we build the trays with the wood, and after like 3 or 4 months it tends to bend. And after implementing, we have this challenge, which is like a kind of obstacle for us for sustaining the technology. One is the food habit. We people in our country are not uh, adapted to eat dried fruits like banana, pineapple, jackfruit. We prefer to eat it fresh. And for vegetables, we hardly, and I never see that any people drying tomato. But for our intervention, they tried some cabbage and bitter gourd, but the price is there is no market demand, and there is no that much. Uh, they're not familiar with the taste, and they didn't do it much, and too much dependency on the project support. There's another thing that that's a very tough challenge for us. people kind of have a perception that when it comes to anything comes to the project people will be responsible for its take care, like for every step. So they hardly take any initiative, even for a very small repairing. And when it comes to invest, they always go back to the alternate or traditional easy way because they find it, I mean, it's working and they are not much concerned about the food hygiene because they only judge the food by their eyes. Like everything looks good in their eyes, they perceive it's okay. And the problem we are recently facing the weather condition now, because usually in winter in Bangladesh we don't have rain, and rain is, I mean, sorry, yeah, in winter we don't have rain, and winter is the kind of good season for us to dry. But nowadays we find that even it's raining even in winter, so people couldn't dry. Even it's also hampered their cultivation practice. And like I said, for the wood and other things and the lack of good plastic, there is a kind of repairing keep going on, kind of periodic repairing. We have to repair like each 2 3 months, and always before the drying season. So when it comes to repair, people show kind of reluctance, and they end up not doing repairing the dryer by their own. And we couldn't use the dryer, our current design, for commercial because they need more. They need something bigger. Anthony, next slide. And there are some success and opportunities, like at the beginning when we build some dryer in the community, when people find that they need another one, so they take initiative to build by their own without our support. But at the end we did support and he completed it. And like I said in the challenge for making a higher capacity, we tried a bigger dryer, and we tested in a local university, Portugal Science and Technology University, and there we tested it, and we were able to dry 30 kg of fishes, like 10 species of fish, and the drying time was 3 to 5 days. But I believe we could do a 40 kilo because we didn't use all the dryers, all the trays. In this design, the one you are seeing in the screen, it's like 20 feet long, and the tray is bigger, like about twice the usual size. It's each tray is about 6 square feet. And Worldfish, a research organization in Bangladesh, they actually find the community are very effective, and they did scale up. And they also recently they are thinking to introduce this dryer in our coastal area. I think everybody heard about it. We are having a crisis for the Rohingya people, and they are kind of trying to build 26 dryers for the community to support their food security and maybe perhaps some livelihood. Next slide. These are the our analysis. The bottom line is that economic performance of the technology is like the chimney dryer varies significantly depending on the product being dried, like high versus low value crops. When you dry the high value products, the profit is higher, and in that case, it can suppress the upfront cost. So for us, two dryers, like two sides, they dried one side dried fish and another side dried pulses, and they actually started profiting even after the second year. And the other side, they are trying some new product. As I told that we don't have, we are not used to eat some certain dried fruits, dried crops like cabbage, gourd, and banana. And they did try this, and when it comes to economic analysis, we found that this side are not, economic. I mean, they are not doing economically profit. So I think this is pretty much about my slides. Thank you.
Thank you, Rana. Thank you, everybody. As everybody can see, we've gone over time, and I appreciate people sticking with us. If you want to stay with us for a little bit more, maybe we can answer a couple quick questions. and then we'll wrap things up. So I have one quick question that's definitely towards Kent. Somebody asked, are the seeds dried with drying beads safe for human consumption?
Yes, they are. The drying beads themselves are crystalline. It's like a china teacup or something. In other words, it's basically inert. So there's really nothing transmitted to the seed. And the reactivation temperature for drying beads is quite high. So essentially it would be sterilized in the drying. But there's no food safety issue with the drying beads themselves.
Excellent.
You can mix if you want to be very quick dry, you can mix the beads together with the seeds and screen them out later. But in some cases that is used, as I mentioned with the hybrid seeds and so on. That's what they do. They just mix it. It's very simple to screen them out later. But a lot of cases that's an extra step. It's not needed, and so you really don't mix them. You just have separate containers, either mesh bags or these central columns or something, and then you're really not having direct contact between the beads and the product.
Very good, thank you. Another question is, are there simple ways that one can check for aflatoxin contamination?
Yes, so there are aflatoxin test strips available from Mobile Assay. And they cost about $15 each.
Per test?
Per test. I believe you grind the product into a little testing application, and then you use a phone application as well to do the test.
Very good. Thank you, Anthony. And then how about we'll do one more last question. How to protect the cereals that, how can you protect the cereals at a large scale from high relative humidity, as farmers in developing countries can't afford hermetic bags?
Well, I'll take a shot at that. Now we realize that that's a problem, and I think that's an issue that has been surrounding PICS bags and others. That is, if you try to put the cost onto the farmer and encourage them to do the drying, they just lose weight and pay for the bag besides. So it really is not to me, the most economic strategy. I think we need to think in the other sense. For example, we're working with Mars Incorporated doing a small project in India right now. Mars has a big issue of aflatoxin in peanuts. They're the biggest peanut buyer in the world. Aflatoxins are big in peanuts, and they have a big problem. They can just accept that and reject 70% of the peanuts that come in as unacceptable, or they could invest in downstream, that is helping to provide containers and bags to help the farmers dry and then maintain that product, and then they get much higher level of quality product. And as in the seeded business, those bags would come back to them. In other words, they could be responsible for recycling them, sending them back to the farm, and so on. So I think it would take my own view is that we need to rethink the supply system. The onus shouldn't be on the farmer. The onus should be on the upstream. 60% of the value in those commodity streams is in the middle. It's not in the farmer. It's not at the end. So I think we need to rethink the value system and put the onus on those upstream who will get value from improved products, less waste, loss, and so on, and encourage them to be the suppliers of those technologies upstream. Also, great opportunities for entrepreneurs. My vision would be there are many entrepreneurs that go to farms to thresh grain or provide different services. They need portable dryers and packaging, and they leave the commodity there in a package rather than just dried but open to the air.
Very good, thank you.
One critical thing, and that is many of these technologies are reusable. The hermetic bags can be used for 2, 3, 4 years, something like that. So they're particularly valuable for a product that a farmer saves back for his own family's consumption. The DryCard's reusable. It can be used many times as long as it's not exposed to very high humidities, above 95%, or liquid water. It can be reused many times. So these technologies, economics look quite good because of that.
Thank you for that, Jim. That's a good point. Well, we've run out of time. Again, I wanted to thank say thank you to our panelists and thank you all for joining. I wanted to remind everybody that in the invitation for the webinar, we included some helpful links for more information about the dry chain and some of the technologies that we've discussed here. There will also be a survey that we've designed to help us learn more about your interactions with the dry chain that will appear once the webinar is complete. If you could take the time to complete the survey, that would be greatly appreciated. I'm looking forward, or we're all looking forward to seeing you all at the next Horticulture Innovation Lab Network webinar, and thank you all for joining.